Hello, everybody. Today we're going to talk about systems in the time domain. We've previously talked about signals in the time domain. Now we're going to move on and talk about systems. And to get started, let's talk about the differences between analog and digital, or we could say maybe continuous time and discrete time systems. This is probably an overgeneralization, but I'm going to use this here just as a generic description. Let's start with the analog systems. The analog systems, well, the category of systems that I'm depicting here are systems like this circuit. This is actually a radio receiver circuit called the Soft Rock 40, and everything that you see pictured there soldered to that circuit board is an analog component. There are resistors, capacitors, transistors, some inductors, diodes, other sorts of things here. So this is an analog circuit, and you would use your continuous time analysis techniques to understand what's happening here. Recognize that, in my opinion, the limitation of analog systems is that, and there are some advantages as well, but one of the limitations is that the number of functions that you can realize is limited by your how clever you are, how cleverly you can combine the basic circuit elements and build up larger and larger systems. And people have been amazingly imaginative and creative, and there's a lot of great analog systems and continuous time systems out there. But let's compare that to a digital circuit or a discrete time system. And here the story begins with a C program, for example. It could be another language, but let's talk about all the kinds of things. Imagine all the kinds of things that you can do to a sequence of numbers using a C program. And if you write that C program, you can compile it and then download your code onto a microprocessor and run that code. That code might run real time and process signals in real time, like the radio receiver you see on the left, or it might process offline. The sky's the limit. So anyway, this is the pipeline that you can think about when you're thinking about discrete time systems. They're systems that can be implemented on a computer, a microprocessor, or maybe in an FPGA, or even an application-specific integrated circuit. But the point is that you have the full flexibility of programs and programming languages at your disposal in discrete time systems. In this class, we will focus mainly on those systems that can be described by difference equations, but whereas in a previous class you focused on systems that can be described by differential equations. Well, we're moving up to difference equations, but recognize that there's a lot of other things that you can do in the discrete time world. Maybe that would be impossible or extremely difficult to do in the analog world. So let's talk about discrete time systems. What do we mean when we say system? Well, a system is a box that has an input and an output. Now, you could actually extend this and say maybe there are multiple inputs and multiple outputs. But let's focus our attention on a single scalar input and a single scalar output. And that discrete time system implements a function. Well, let's take a closer look. So that function has two arguments. The first argument is the input signal. And notice that it's not just one sample of the input signal, it's all the samples of the input signal in general. And the second argument is a time index. Basically, it's the time at which we wish to compute the output. So this function, which could be a time varying function even, but what happens is when you decide what time you want to calculate the output, you then go through and look across all the samples of the input to the extent that you wish, and extract and perform calculations on those samples of the input signal to calculate the output. We'll look at some examples in a minute. But to add a little bit more definition to this, I have given that the output time index is n, I have written in some of the samples surrounding that time on the input. So xn is the input at time n. That we would call that maybe the current input sample, because that's the sample that appears at the input at the time that you want to calculate the output. So that would be maybe be called the current input. And then all of these samples over here, maybe we could call those the future. Those samples at time n haven't even occurred yet. And then these samples over here, these would be samples that are in the past. That's in the history. So maybe we're saving all these samples in a buffer or some memory somewhere. So we have the past, we have the present, and we have the future. And again, that's all relative to the time at which we're calculating our output. So now think about any mathematical function that you could perform on these samples, and that's a discrete time system. Here are a few examples that will be useful for this class. The first is an identity system. It doesn't do anything. It just passes the input at time n to the output. This one is an amplifier. It just multiplies the input by some scale factor and outputs the answer. This one is a delay system. It has some memory and remembers the last d samples, where d is an integer, and it returns to the output the sample that was observed d samples ago. Here are a couple of examples called moving averages, because they average together. There are three terms, and they average together the current sample, in this case, the current sample and the previous two samples from the history. So we add all those together, divide by 3, that's an average. And it's called a moving average because as the time index runs forward, the samples that are falling in the averaging window move along with it. So it moves. Here's another moving average. Notice that in this case, the current sample appears in the middle, and then we take one future sample and one past sample, and we average those together. The next example system is called a median filter because it takes the present sample, a future sample, a past sample, and then returns the median of those three. And if you're not familiar with the median, the way you calculate the median is you sort these from smallest to largest, and then you select the middle one. That's called the median, and you return it to the output. The next example is called an accumulator, sometimes also referred to as an integrator, but that's probably an abuse of terminology because an integrator is something that is encountered in continuous time. An accumulator acts like an integrator. What it does is it just adds the history of samples together. And that's what you see here, x of n plus x of n minus 2, n minus 1, n minus 2, and so on, back till time in negative infinity. You could write that in a recursive form if y of n minus 1 is the sum of all the samples up to time n minus 1. You could get the updated accumulated value by just taking the old accumulated value and adding the newly observed sample. These summations show you two other ways you could write down the same thing. Let's move on to a few other examples. Here, this next example is called a rectifier because it takes the absolute value of the input and sends that to the output. The next example is called a compressor. It selects one out of every d samples and passes it to the output, throws the others away, and so that compresses the signal. The opposite of that is expanding, and this is the math that describes an expander. And then finally, we have a modulator, where you take a signal x of n and you multiply it by a discrete time sinusoid, cosine 2 pi f n. We'll call that modulation. Now we're going to have 4 different characteristics for systems. The first one is causality, and we're going to modify only slightly what the function can do, and we arrive at causal systems. So a causal system is one where the output depends on the current input, the present, and the past. But notice that it doesn't depend on any future samples. In that case, the system would be causal, or sometimes it's referred to as non-anticipatory. In causal signal processing, you can't observe the response before the excitation occurs. And so all of these sorts of things are relevant with causal systems. Of the examples that we were just looking at, which ones are causal? Well, the identity system, the amplifier is causal because, again, just look for future samples. If there's any future samples over here, then it's going to be non-causal. Here's the delay system. Now, notice that if the delay D is a positive number, or 0, then the delay system is causal. But if the delay D is negative, then the output is actually equal to one of the future samples, a sample that hasn't been observed yet, or it's observed D samples into the future. Of the two moving averages, one is causal. Notice that this one depends on the present and 2 past samples, whereas the second moving average depends on a future sample, and therefore this would be a non-causal moving average. The median filter that we described is a non-causal system because it depends on one of the future samples. Of course, you could define a causal median as well. The accumulator is causal because it doesn't depend on any future, it only depends on the past. The rectifier is causal, and the modulator is causal. The next characteristic of a system that we're interested in is stability, or in this case, bounded input, bounded output stability. A system, or rather a signal, is bounded if, when you take its absolute value, it's always less than or equal to some number, some real number m, and that number is not infinity. So that would be a bounded signal. A sinusoid, for example, is a bounded signal because it never exceeds plus or minus 1. A constant is another example of a bounded signal. The unit step function is a bounded signal. A system is said to be bounded input, bounded output, stable, or we'll usually just simply say it's a stable system if the output is bounded whenever the input is bounded. So the two moving averages that we've seen before, those are bounded, and so, or I'm sorry, those are stable systems, because if the input is bounded, let's say the input is bounded to be less than or equal to 1 in magnitude, then the output can never be larger than the sum of those three values. It can never exceed some other bound. It might be a bigger bound, but it's still bounded. The median filter is bounded, is stable, but this accumulator is unstable. And as an example to show that it's unstable, let's find a bounded input signal and see if we can make the output become unbounded. If you let the input be the unit step function, that's obviously a bounded signal. It's never larger than 1, and it's never less than 0. That's a bounded signal. If you put that into the accumulator, however, the output ramps and therefore becomes unbounded. You can't find a number m that bounds the output because you can always just move forward in time, and the output will eventually exceed whatever bound is put in place. So we have stable systems, we have causal systems. The next property is linearity, and I'm depicting that here just in pictures. So if y1 is the response of the system to x1, and if y2 is the response of the system to the input x2, then if we put in a times x1 and b plus b times x2, that is, we're adding these two together with scale factors, the response would need to be a times the response to x1, which is y1, plus b times the response to x2, which is y2. So if the system obeys this kind of a property, given that these two things are true, then the system would be said to be stable. This linear combination extends to an infinite number of signals. So it's not just finite combinations, it also needs to be infinite combinations as well. Sometimes this is referred to as superposition. So linear systems obey superposition. One other simple test to determine if a system is linear is to put in 0. If you put in a 0 to a linear system, you should get out 0. Let's look at our example systems and see which ones of these are linear. The identity system, the amplifier, the delay system, the moving averages, those are all linear. The median is nonlinear. And it just so happens that when you sort these and select the middle one, that's not a linear operation. The accumulator, I wrote causal here, that should say linear. The rectifier is nonlinear, and the modulator is linear. Let's move on. The fourth property is time invariance. And essentially, I'm using a picture to replace the definition. The definition is that if you delay the input, then the output has a corresponding delay. So this property has to be true for all n, which is the time index, and for all possible delays d. Essentially, the characteristics of the system do not change with time, so it's time invariant. Of the examples that we have looked at, here are some that are time invariant. The delay system, the moving average, the median, the accumulator, the rectifier, but the modulator is time varying. You can tell by just looking at the coefficient. The nature of this system, the coefficient that we're multiplying by, is a time varying coefficient, and so of course it's time varying. In the future, in this course, most of our discussion will deal with systems that are linear and time invariant, and the systems that we'll actually implement are causal and stable. So generally we're interested in causal, stable, linear time invariant systems, and we'll abbreviate in the future linear time invariant systems with this LTI acronym.